Hello and welcome. My name is George Minich, and I will be chairing this session. And our first speaker is Xenia Ossa from Oxford. And the title of the talk is Periods, Black Holes, and the Arithmetic of Calabi-Yau Manifolds, Part 1. Xenia, please.
Well, first of all, thank you so much for the invitation, and I mean to the organizers for organizing this meeting. So today, Philip and I will give you two talks. I mean, on as the title says, about the relationship between periods of Calabi-Yau manifolds, black holes, and the arithmetic of Calabi-Yau manifolds. So the relationship is like in this triangle here. Right, so in one corner, we have the geometry of Calabi-Yau manifolds, and mathematicians and physicists know why they are interested in them, right? An important fact in this talk is that the complex structure of the Calabi-Yau manifold is determined by the periods of holomorphic 3-0 form, and I will be more explicit about this later. If you are a number theory, you are interested, a number theorist, I'm sorry, you are interested in the arithmetic of algebraic varieties, right? So we are going to be interested also in the arithmetic of families of Calabi-Yau manifolds and its modularity properties. And this again, I will be more specific about what that is. And as we will see, there is a close relationship between these two corners. So the first talk will be mainly about this first part here. And then in the second talk, Philip will relate this to string theory, but in particular to the physics of black hole solutions in type 2 string theory. And this is joint work with Philip and Mohamed Elmi, Duco van Straten. So there are two papers and another one with Philip and Duco. And as he will tell you, I mean, there is a beautiful relationship that one can find that relates the entropy of a black hole with certain arithmetic quantities called L values. So this is, I mean, a nice picture of these my collaborators, Philip, Mohamed, and Duco, eating in Korea. So it's very nice. So this is more or less the content of my talk. I will give an introduction of a few facts of Calabi-Yau manifolds, those that will be more relevant for us. Then I will talk about the arithmetic of Calabi-Yau manifolds. And then I'll talk about modularity properties. And the next talk, as I said, Philip will talk about black holes, in particular the attractor mechanism and modularity. So let me start with very general facts about Calabi-Yau manifolds. So as we know, I mean, Calabi-Yau manifolds are compact scalar manifold with vanishing first-term class. In these talks, we are going to be concerned with the case of 3 complex dimensions. So a very important fact, which you can take as a definition, really, also for the Calabi-Yau manifold, is that that there exists a unique up to a constant 3-0 form that I'm going to call omega, which is holomorphic, right? This. So what this means is that if you consider the third cohomology groups of these manifolds, what you find is that dimension of H20, or equally the dimension of H03 is 1. So the other important fact is that Calabi-Yau manifolds have parameters. They come in families, right? So we know that they have a complex structure, and they have a Kähler class because they're Kähler manifolds. Most of our talks are concerned with the complex structure of the Calabi-Yau, right? So this parameter here, this denotes a generic complex structure parameter. Right? But we should never forget that they also have parameters associated to the Kähler class, and that of course mirror symmetry relates this. So as I mentioned earlier, that periods determine the complex structure. So let me be more specific about what that means. So there is, in fact, a canonical way to give coordinates on the space of complex structures, right? So consider, as I said before, omega, that is defined up to a scale, but is otherwise unique, right? So it defines a line in H3, right? Just as in this picture, right? Defines a line inside H3. So we can study one way to study the variation of these complex structures is by studying how omega varies inside H3, right? So how it moves inside this space. And the coordinates of this line, on this line, right, are precisely what we call the periods of the holomorphic of the three form. So more precisely, right, consider a symplectic basis of the third cohomology or the third homology, right? Alphas and betas here are a basis of the third cohomology group, right? Of course, the dimension of H3 is P3, which for the Calabi-Yau case, this P3 will be 1 plus H21 plus H12 plus H1, where this is the 2-1 Hodge number, and these two are the same, right? So A and B here go from 0 to H to 1. And symplectic means that this basis satisfies this satisfies alpha 0, and similarly for beta. We have we also have the dual basis, right, of capital A's and capital B's here of the third homology. And again, we have a symplectic, we can choose a symplectic basis. And in this case, what it means is that the intersection of A with B is 1, and the intersection of A with A is 0, and so on. Similar for so given a symplectic basis of the third cohomology group, one can write down the holomorphic 3-0 form as a linear combination of these bases with coefficients ZA and FA, right? So the periods, what we call the periods of the holomorphic 3-0 form are the integrals over the homology basis of omega, right? If you integrate omega over the A's, right, you get a Z, right? And if you integrate over the B's, you get one of these coefficients here. Right, so these Z's here, you can take them to be homogeneous. You can take them to form a homogeneous coordinates on the moduli space, right? So these and the F's are in fact, one can show that they are derivatives of an object called the holomorphic potential, and this is what we call special geometry of the moduli space. So so these periods, as I said, determine the complex structure, so determine the geometry of the complex structure moduli space. And the geometry of these spaces is rather interesting. It's called special geometry. So the parameter space is itself scalar, and with an extra structure that it exists a holomorphic potential. So all these facts are well known. I won't prove any of these, right? But we need to keep in mind, particularly the fact, right? That we have these periods for the holomorphic 3-0 form. So Philip later will need a little more than just the periods. I mean, the moduli space is scalar, right? So that means that the metric is the second derivative of a scalar potential, K. So this is the metric on the moduli space, where K is in fact given by the exponent, the exponential of, so e to the minus K is given by I omega which omega bar, right? And it's also the dimension of this space is H to 1, as we know. So mirror symmetry, I mean, I won't discuss mirror symmetry in these talks, but we know that that the moduli space of complex structure is of a Calabi-Yau is isomorphic to the moduli space of the Keller class parameters of its mirror. So this is just in parentheses for us today. So, okay, so I've just said that the periods of the holomorphic 3-0 form a homogeneous basis. You can choose, you can take them to be homogeneous coordinates on the moduli space of the complex structure. But what comes next is the fact that you can compute them. In fact, they satisfy a differential equation called the Picard-Fuchs equation. And the degree of the operator, this is a linear operator, differential operator of degree B3. So B3 is the third Betti number. So they are computable. I mean, there is a prescription to find the Picard-Fuchs equation, due originally by Dwork, and then later on Gelfand, Kaplanov, and Zelevinsky elaborated on Dwork's work and produced a sort of algorithm to produce the Picard-Fuchs equation. Now I'm making it sound that this is easy, and it isn't, right? So, but in practice, one can do some computations. In particular, what I will focus today, or Philip too, on one parameter families of Calabi-Yau manifolds in which H to 1 is 1, right? So only one complex structure parameters. So that means that B3 is 4. So these differential equations will be of degree 4. These operators are rather nice. They are Fuchsian. So this is a Fuchsian differential equation. That means that the singular points correspond to regular singularities, right? So that's nice. Okay, so that's facts about Calabi-Yau manifolds. There will be two examples in these talks. One is the quintic that we all know, right? Which is the quintic Calabi-Yau, which is given by a quintic polynomial in P4, right? For example, this is an example of a quintic polynomial in P4, but the xi's here are homogeneous coordinates in P4. This example has one Keller class parameter and 201 complex structure parameters, which means that P3 is 204. But the mirror of this manifold has these numbers reversed, of course, right? So H21 is 1 and H11 is 101. And as it is well known, one can obtain the mirror quintic by taking quotients with respect to some automorphism group of the quintic and then blowing up the fixed point singularities. So this is one example that we're going to talk about. And the other example that will take more of a role in next talk is an example that was constructed by Hulick and Beryl. So it is one can the proper description of this manifold is actually given in terms of toric as hypersurface in toric varieties. So I will just give you a simple description that is valid when none of the coordinates you take coordinates in P4 that are non-vanishing, and you can describe this manifold at least when none of these vanish, none of these coordinates vanish as by this polynomial, right? So we have one parameter here, and we have here the product of a linear and 1 over and the sum of 1 over x, like this. So this if you work with this manifold, I mean, you will discover that there are in fact singularities where some of the xi vanish, but you can blow them off nicely to obtain a smooth Calabi-Yau manifold. And what you get is a Calabi-Yau manifold with h to 1 equals 5. And to obtain a one parameter family, what you do is to take the quotient by a Z5 or a Z7 or a C10. this is a Z5 symmetry, and this is a Z2 symmetry. So you can take the quotient by just this one. So this is just changing xi for xi plus 1 for all i's, right? So you can take the quotient by this and get a one parameter family, or you can take a quotient by these two and get another one parameter family. And all that the changes is H11, where you do one or the other. Right. So for these cases, the Picard equation is known, right? So for the printing, it has been known forever. And for the Hurley-Canberra manifold, Hurley-Canberra actually wrote this down. So this is, as I said before, we will have a polynomial, a differential operator of degree 4, right? Which will have this form where theta is the logarithmic derivative with respect to the parameter. And these SIs here are polynomials in phi. Right, for the quintic, the differential equation has only 3 regular singularities at 0, infinity, phi equals to infinity, and phi equals to 1 over phi. So this one here corresponds to a manifold that has an isolated singularity, which is an ordinary double point, which physicists call a conical singularity. This one here, this is a rather nastier singularity, which is called the large complex structure limit, right? And it's a point of maximal unipotent monodromy. So this one is the Fermat point, right? Which is smooth, but has an extra symmetry. So apart from these values, this quintic is smooth, right? Apart from 0 and 1 over 5. The Hurley-Canberra has other features, right? It has not just one conical singularity, but has 3, right? That these values of phi, 1, 1 over 9, and 1 over 25. Phi equals to 0 is the large complex structure limit. And otherwise, is the manifold is smooth, but also, I mean, apart from infinity also. So why this example? I mean, it looks like, why would I choose that example? That is, as you will see next talk, it is, I mean, Philip got to tell you about the fun part, really, right? Which is this manifold exhibits interesting arithmetic properties which have an interpretation in black hole solutions of string theory. Yeah. So I think that's all the facts I need about Calabi-Yau manifolds. Is there anything, are there any other questions? Are there any questions at this point? No? Okay, so the arithmetic of Calabi-Yau manifolds. So let's suppose that we have a family of some algebraic varieties, perhaps Calabi-Yau manifolds, right? Such that the manifold is described as a Calabi-Yau that is a hypersurface with a defining polynomial P, right? So this is the complex structure parameter. But let's suppose that we take phi equals phi in Q, the Q being the rational. And I mean, if you're a number theorist or a mathematician, and a very natural question for you to ask is how many solutions of the polynomial are there over Q, right? If the solutions where xi belongs to the rationals too. And the next question that you will ask as a mathematician is how does this number vary as you vary phi? So a physicist maybe has no reason to ask for this. This is too hard of a question. If you are a mathematician, you know this. I mean, you will know this is just this is much too hard, right? This is hard even for the case of, say, the elliptic curves, right? Where this question led to the Birch-Trinenthal-Dyer conjecture, for example, that gives you estimates about these solutions, right? So, however, it makes sense to reduce the problem mod P, right? Where P is a prime number. In other words, is to work over finite fields. Right? Finite fields, of course, are classified. This object here is a finite field with P to the K elements right? Where k takes values is a natural number. So finite fields are just like the fields that we know well, like the rationals, the reals, or the complex numbers, except that they are finite. They have a finite number of elements. And the simplest, of course, is Fp, right, where k is 1, which is the set of integers. So you can think of Fp as a set of integers mod p. Right? And one can still learn a lot, right? So let's suppose that phi takes values in a finite field. So the fundamental quantities of interest for a number theorist are these numbers n sub k, which is the number of solutions of the polynomial over the finite field. And this number here, there is a for these numbers, for these quantities, there is a generating function, which is the zeta function. The zeta function, which is, this is the definition, right? It's an exponential that contains these numbers. The t is a formal variable, t to the k over k. Note that I won't always write this, so not to clutter the notation, but keeping always in mind that if one is computing the number of points, is this number here, this number depends on both. I mean, on the prime here, and it depends on phi, right? So you expect this object to vary with p and phi. The simplest case is when your variety is just a point, right? And you think that is boring, this is ridiculously boring. I mean, the number of points in that case is always 1 for all case. And then you put 1 in the exponent here. Let me see if we can see, but you put 1 here, right? 1 here, and this of course is minus the logarithm of 1 minus t, and the zeta function of a point is 1 over 1 minus t, right? Couldn't be any more point. But now look what happens. Now let's consider the product over all the primes of this object evaluated when t is p to the minus s, right? This is a real, right? But this can be extended to complex numbers, but let's consider a real number here. So these I mean, Euler told us, I mean, this step here is obvious, right? Just evaluate this here. But then Euler told us a while ago that this product here, this is the Euler product of this series, right? The series from n, the series of 1 over n to the s, right? Where n goes to 1 to infinity, right? And this gives you nothing but the Riemann zeta function, right? So here, when we go from the local zeta function for a given prime, and we take the product over all the primes, then we go to what is called in number theory the L function, right? And eventually we are interested in the L function of this of Calabi-Yau manifolds. So more generally, the zeta function satisfies a number of properties. These were first stated as Wahl conjectures, which became theorems later on. And this was extremely important work last century. An important property is that the zeta function is always a rational function. This was proven by Dwork. Meaning, of course, that this is a ratio of two polynomials over the integers. There are two other properties that is called the functional equation and the Riemann hypothesis that were proven respectively by Grothendieck and Deligne, right? So that you can just see them in the slides. I mean, D here is the dimension of the algebraic variety, and chi is the Euler number of the algebraic variety. And the Riemann hypothesis says that these polynomials in the numerator and denominator of your rational function factorize further over the integers, right? So these Ri's are polynomials with coefficients in Z, and the degree of each of these is bi, where bi is the ith Betti number. So notice that the factors in the numerator have the odd Betti numbers, and the factors in the denominator have the even Betti numbers. The Wahl conjectures have they say more. I mean, they also tell you a bit about the roots of these factors here. So also notice that this first one is true even if your algebraic variety has singularities. These two aren't true, right? You have to work harder to make statements of what happens when your variety is not smooth. So now we have the case of 1 point. So a very famous example, right, that has been the subject of research. Again, my number here is a lot of research. Is this, of course, the elliptic curve, right? So which is a Calabi-Yau dimension 1, and using the Bell conjectures, what you find is that the zeta function has this form. This AP, this coefficient here, is minus the number of points over FP. Right, and this is true as long as P is not a prime of bad reduction. That means that your elliptic curve defined over P is not singular. Is not smooth. So for the smooth cases, this is true. So also a very important fact is that the elliptic curves are all associated to modular forms. Right, this has to do with the Taniyama-Shimura conjecture proven by Wiles, Rudel, Conrad, Diamond, and Taylor. Right, and I can make a brief statement about this. I mean, you can consider again this local zeta function and evaluate T, P to the minus S, take the product of all the primes. And then you get a series, right? But now you have some coefficients here. And these coefficients are the nth coefficients of a modular form of weight 2 of the congruent subgroup gamma 0 of n, that's subgroup SL2Z, and n is called the conductor. And it's a number whose prime factors are the primes of bad reduction, right? So the elliptic curve is singular. Right. So this is a very an incredibly beautiful statement about modularity of elliptic curves, right? So if one is working now with threefolds, so what do you want to say, right? When you're working with threefolds. So for threefolds, again, the Bell conjectures tell you that the zeta function has this form, right? So this is B1 is 0 and B5 is 0. So R1 here is 1 and R5 here is 1. So this polynomial here has degree B3. And then in the denominator, we have 1 minus T and R2, R4, and 1 minus PQT, right? Where R2 has degree B2 and the same for R4, right? Which is equal to H11. Because H20 and H02 is 0 for the Calabi-Yau manifolds that we are considering. So that's the general form for smooth Calabi-Yau. So for the mirror quintic and the Hurricane barrel, B3 is 4, right? So for values of pi where they are smooth, right? It has this form, right? Where this is H11 and H11. And R0 is a polynomial of degree 4. And again, using the Bell conjectures, you end up with that the polynomial of degree 4 has this form. So you have 1 plus a coefficient AT plus another coefficient B PT squared. Then the coefficient of the term TQ is apart from this factor of PQ is the same as this one. And then you have P to the 60 to the 4th. And you discover that this A is minus the number of points over P, and B here is apart from this factor that it contains in 1 square, is minus n2 the points over F, the finite field with P squared elements. Okay, and of course, I mean, what happens when there are singularities? Something happens, and I will give you an example later. So, okay, so I started in the first section, right? I told you about Calabi-Yau manifolds and periods and how important they are to understand the complex structure of Calabi-Yau manifolds. And now I've told you about a story about the zeta function and counting points over finite fields for Calabi-Yau manifolds. So what does that mean? What do all these have to do with periods, right? So they said there would be a relation between these two. I mean, the real relation is deep, is buried in the proof of the Bell conjectures. In fact, of course, we cannot go over that. But there are very nice, one can in fact, so we have these A's and these B's. So these can in fact be computed in terms of the periods, and with some effort, you can write explicit formulas of these numbers in terms or these coefficients here in terms of let me say, in terms of some arithmetic version of the periods, right? So so we wrote this down we wrote these explicit formulas a long time ago. I mean, over 20 years ago, with together Philip and I and Fernando Rodriguez Villegas for the quintic. These formulas, these explicit formulas for the periods, I mean, they are technical, and this is why I am avoiding writing them up. Are easier to write for the quintic than the Hurley and Barrow manifold. But there is more. I mean, we're able to go further, in fact. There is another way of writing this polynomial, which is in terms of an object called the Frobenius. So you can recast this polynomial in terms of the determinant of a determinant that involves an object called the Frobenius map, which is a map between acting, in this case, for this particular case, acting on the circle homology, and is constructed from the periods too. So this object comes from an automorphism that's called the Frobenius, that exists for all algebraic varieties defined over finite fields. And what we did with Duco in a paper, a rather large paper that we published in April this year, we showed how this object could be computed very quickly, right? Using this object here. I don't want to get into any. I mean, the moment I say anything else becomes rather technical, and I think I just leave it there, and this will appear again in Philip's talk. I mean, when he talks about the attractor mechanism and black holes. So question number one: what are the arithmetic properties of R0? Right? We can ask questions analogous to those that were asked for elliptic curves. In particular, those of these coefficients A and B. I mean, that is there an analog of the modularity of elliptic curves for Calabi-Yau threefolds? And this you are now throwing yourself into the realm of the Langlands problem. So these are again at this time very, very hard questions. This modularity, when I say modularity here, it's an analog modularity. This is not a classical modularity that we're talking about. It's a much more complicated notion that becomes classical except in special cases, like rigid Calabi-Yau manifolds. That by rigid I mean Calabi-Yau manifolds that where H21 is 0, right? So the complex structure is rigid. There is also work about modularity on Calabi-Yau manifolds by Shamit Kashu and Richard Nally and Wenger Yang, right? That is also extremely interesting, and I was hoping that Shamit would speak about that. Already spoke? I don't know. So anyway, so what can we understand, learn about these coefficients? I mean, what we have done, I mean, as you will see next talk, is that that very interesting happen that one can learn, I mean, from techniques we already have for special values of phi. So as I said, generically for the smooth values of phi, you have this, right? But for certain values of phi, something interesting that one can understand might happen. that is not as hard as trying to go into the pull into the Lagrange problem. Okay, so this takes me to the last part of the talk, which is about singular cases, the L function and modularity. So I already mentioned the conical singularity, right? So for example, for the quintic, right? This is was a quintic polynomial, right? There is a singularity when phi is 1 over 5. So as I also mentioned before, the zeta function is still a rational function, but the other back conjectures are not true anymore. But you can compute the zeta function, right? Using the techniques that I mentioned earlier, though I didn't describe them. And what you find is that R0, instead of being of degree 4, now becomes a polynomial of degree 3 that factorizes further into a linear and a polynomial of degree 2. Right, and again, so now you only have one coefficient, AP there, and what you find for the particular case of the quintic is that this AP is also this modularity in this case. AP is the pth coefficient of in the Q expansion of the eigenform G found by Shen a while ago. So it's a unique Cobb's form of weight 4 of gamma 0 of 25. Right, and if you want to see it, there it is. You want to see the modular form itself. And in this case, you can ask, well, why, right? Why would you have modularity there? And then at least you can answer this mathematically using the work by Goubert and Yui, right, that prove modularity for rigid Calabi-Yau manifolds defined over Q. What happens is that this conical singularity is on the boundary of the moduli space of a rigid Calabi-Yau manifold. So they share the zeta function, and the same modularity appears at that point.
Xenia, you have 5 minutes.
Thank you. So so a similar behavior appears for the Hulle-Cambero at the conical singularities, and this has already been pointed out by Hulle-Cambero themselves in their papers. So this modular behavior of conical singularity seems to be generic, not just associated to rigid Calabi-Yau manifolds. There is something else, that this behavior can be understood geometrically. I mean, we know what's happening geometrically as you approach a conical singularity, right? What is happening is that you have 3 cycles that are collapsing to a point. You have vanishing cycles are collapsing to a point, and so at least superficially speaking, right? What happens is that some of the roots of the degree 4 polynomial vanish. And then the polynomial reduces to a polynomial of degree 3 in this case. So, but there are many questions. I mean, I can tell you this, and it raises more questions, right? What is the meaning, if any, of this modularity in physics? I mean, conical singularities are places where a lot of fun happens, right? Physically in string theory. So what is the meaning of this modularity in physics? I don't know. And what happens at other singularities, right? What happens there? And for this one, we'll have to work with Calabi-Yau manifolds with more parameters, right? And see, try to study what happens. So finally, let's see what I can tell you about the L function, right? Again, we consider the product over all the primes of R0 evaluated at p to the minus s, I mean inverse. And except for bad primes, as I said, R0 is this object here. But for bad primes, we can always find what R0 is. We can always compute it. And about over 10 years ago, together with this group of people, we actually studied numerically the prevailing conjecture about modularity for this function. And what happens there is that you consider what's called the complete L function, which is the L function up to some gamma factors, right? And a conductor here. And the conjecture for the quintic, at least for the quintic, is that this is a mouthful that makes me break into a sweat when I say it, right? Which is this, one wants to compare this with the spin or L function of a genus 2.3 spin or Siegel modular form of the Langlands dual of SP4. So yeah, I cannot even begin to explain what this is, right? So I just wanted to say the mouthful to give you an idea of that this is not the usual classical modularity that we are talking about. So, and not much is known about these subjects, in fact, but there is the people are working very actively in this. So we did numerical tests. I mean, if this is true, then this conjecture tells you that this complete function will satisfy a functional equation of this sort, right? 4 minus s and s here. And we tested this and it works, but this just, that doesn't do anything yet. And there have been tests for other Calabi-Yau manifolds ever since that work in 2009. Okay, so now I'll finish with an epilogue, right? Just to introduce, so Philip, in his talk, he will talk mainly about the Houlihan-Beryl manifold and modularity and black holes. And what he will show you, he will discuss, is that at certain values of phi star, where the Calabi-Yau is smooth, so there's no singularity, these R0 factorizes into 2 quadratics. And that one quadratic resembles very much the quadratic polynomial that appears in the cases of elliptic curves, and the other piece resembles what happens for the rigid case. And Serre's conjectures say that these two should be attached to specific to modular forms of specific weight and conductor. And Philip would tell you what this is for this example. Moreover, these points, these special points that have this modularity are associated to attractor points in the attractor mechanism of black holes. And the data of the black holes of the horizon are related to the L function, right? So finally, there is the Hodge conjecture by Hodge conjecture that says that there must be some geometric reason for this splitting. And whereas we understand the geometric reason for splitting in the case for the conifold, we don't understand the geometric splitting yet for this case. We don't understand we don't know how to explain this geometrically yet. Okay, so I think I'll end here and now pass on to Philip up to questions. So thank you very much for your attention.
Thank you, Xenia, for that very nice talk. Questions? Why don't you unmute yourself and just start asking?
Hi, George. Can I ask you a quick question?
Mm-hmm.
Sorry, well, a bit of an echo. We're doing this live here. Sorry. Okay. Xenia?
Yes.
Thank you very much for the beautiful talk.
Thank you.
Just a quick question on your feeling. Elliptic curves are supposed to be associated with modularity of SL to Z, and you've shown here very nicely Calabi-Yau threefolds or SP4. Is there a pattern in general for N? Calabi-Yau?
This is the one parameter case, right? The SP4 is just one parameter case, right? Who knows what happens for more when you have more parameters? Hello, Yang?
Yeah, sorry. So we don't have a pattern yet.
Sorry, I still don't.
Yeah, I don't know what he's doing.
Sorry, I'm just trying to juggle. Is this better?
Yeah.
Yeah,
Sorry, we're broadcasting your talk live here, so we're getting some feedback.
Oh, I see.
Sorry, I missed that answer. So it's not clear that there is a pattern.
I don't know. I don't know anything apart from what I just told you for the one parameter case.
I see.
I have no idea what will happen with more parameters. I just don't know.
I see. No, I can't wait to see more results from you guys. It's a really beautiful story.
Any other questions? I don't see any hands. Let's see. I had a quick question, Xenia. I kind of missed the what's sort of the arithmetic meaning of mirror symmetry? Is there, yeah.
Yes,
Is there...
I actually took out the slides about mirror symmetry because they would have been talked too long. So,
Okay.
so I think I'll show you something. I took them out. So let's, for a one parameter case, right? So this is what we had before, right? For the quintic and its mirror, right? So this is the case I've been discussing, right? So this is the full zeta function. This is the full zeta function for the case I was discussing, right? You have a polynomial of degree 4 here and a polynomial of degree 204 in the denominator. For the mirror, this reverses.
I see.
Right? Of course, you have here a complicated polynomial of degree 204 and a very simple polynomial of degree 4 in the denominator, right? And it's very tempting to say something that this is the inverse of that, because of course that's not true. These zeta functions don't understand Killer class, right? So the ingredients that you put into this is just a polynomial. So they actually know about the second and the fourth Petit numbers, but there aren't any Killer class parameters in here because they're not algebraic. Right.
I see.
Well, right. So this zeta function is not quite mirror symmetric. I mean, so we discussed this here a while ago, but what we discovered for the quintic is that in fact one is the inverse of the other, apart from factors of order 5 squared, and one can in fact write down expressions like this. One can take the polynomial of degree 4 and divide it by the denominator of the mirror, right? And then you obtain a very nice series, right? That from some coefficients that are integers, and we don't know what these are counting, but we suspect they are related to some counting of rational curves in some sense that I can say. And we are thinking about how to understand this at the moment, right? This involves a mirror map, right? This was the arithmetic meaning of mirror map.
Right. It's very beautiful. Wow.
So yeah. Anyway, so that's I have taken this out.
Okay. Well. Okay. I was, I guess,
it was a bit too long. Yeah.
Yeah.
Well, thank you.
Okay. Yeah. Well, thank you for this beautiful talk. Okay, so is Philip going to continue on the same?
Yes, so Philip has been sitting here. So we have to avoid wasting time changing. So what we have done is that we have put both talks into the same iPad.
Okay.
So Philip will continue.
All right.
Here.
Okay. So
can you see his slides?
Yes, I can see the slides.
Okay, so now he will. Well, thank you very much, and now.
Thank you, Xenia. Thanks again.